Okay, a very good morning or afternoon. So, welcome to week 5. So today, actually this week is what we call it as a asynchronous learning. So, so today we will discuss about the continue with what we discussed last week on the granger causality based on the what we call it as a Johansson and Jussius. And we will touch a little bit on the autoregressive distributed lag model. Okay, this is the thing we will cover at the first part. Then we will move forward to the type of the panel regression, which include the pool OS. And the next week we were going to touch on the difference, to show you the difference between the pool OS, pool square, with these random effect models, and also the how we can because beside the random effect, we also got another model test, which is called fixed effect models. Then we're going to introduce you to diagnostic tests, which used to test the whether which one is better models. The different means that the better models. So amongst the pool OS and the random effect, we can use the Bush-Pagan test. We also I also will show you how we can rely on this Hausman test to compare whether the random effect better or fixed effect models better. So okay. So before that, let's take a look my screen now. Actually, this is a continue what we discussed last week. So in the last week, we talked about the co-integration and also show you the general expression for the error correction models, right? So not only that, we also apply the error correction models to test the Granger causality in the short run as well as in the long run. So today we were going to use the Johansson and Jussius and shows you how to use the system, which is under the Johansson and Jussius system to test the Granger, and as well as the Granger in the short run and also in the long run. So before that, let us download the dataset first, right? Yeah. So I need to use back a dataset in my week number 1. So hope you still in the week number 1 there is an Excel sheet which is available in your Spectrum, right? It's actually I draw from the world development indicators. So once you open it, this is for the panel. So I want to open for the another file. Yeah, this is the files. We look at this file first. So this is the file we applied in the class in the past few weeks. So I would like to test the in my model I'm going to have my income, right? Income, interest rate, exchange rate, right? Income, interest rate, and exchange rate. So in my Excel, so I would like to look for the Malaysia case. Yeah, I look for the Malaysia case. Malaysia. Okay. Then you click OK. Then not only the broad money, I need to use the interest rate as well as the gross domestic income, which is present for the proxy for the income. I also need the rate effective exchange rate. So these are the 4 variables, right? These are the 4 variables I would like to use in my to show you to run the analysis. So now that what we done previously, so I would like to copy this data set. I need to rearrange my data set. Okay. So this refer to the broad money. I think I use the abbreviation is the L money, right? Yeah, money and the income and then DIR. So I use money, then I use the income, I use the DIR as well as the RER. So these are my series that I copy all these 4 series, right? Start from 1960 to 2021. I go to the eViews work file here, go to new, right, new work file. Start from the 1960 to 2021, right? And click OK. So this is what we did last week, right? Then I'm to create this series. Then I paste here. So this is my data set in the eViews. Then I need to generate the series. I need to log the series. I use ln money equals to log in the parentheses money. Then I also need to log for my income. Okay. I also need to log for my interest rate. I also log for my RER. Okay, done. So now I run the and click on the LN money, the LN interest rate, LN income, and the LN RER. I open them as a what we say the WAR form. Then in terms of the method, I will click on this what we say the VCM. Okay. Before that, we need to click on the WAR form, right? WAR form. Now I click OK. So in the WAR form, because I want to identify how many lengths, right? I go to View, leg structure for the length criteria. I click OK. So based on the AIC, it suggested me 3, right? Then SC suggested 1. So I will rely on one leg, leg 1, right? Leg 1. I will base on the one leg to perform my analysis. Given me the observation just 39, because this one is a balance, right? Balance sample. So just 39 instead of 62 because I think there one series is actually the RER, right? It just start from 1979. So that's why it's a shorter sample compared to the 62 observation. So it's a one leg. Then what I need to do here is I need to open them as a WAR. But now I change the things, I change the method to become VEC, factor error correction. That is a one leg, so I use 1. After that, I click OK. Right. So once I click OK, this is my vector error correction estimate. So this is my long run result. Long run result and income has a positive impact on the money. Interest rate is a negative, and actually they are significant, right? Significant, but the exchange rate seems not significant, but it's a positive impact on the money demand. Then what I interest here is to use this what we say this Johansson and Juseris to estimate to answer the question. If the question asks you, is it the interest rate granger cost the money in the short run and long run with the eViews? So how I can use the Johansson and Juseris help me to answer this question. If based on the error correction models, is it right? Look at the ECT term, right? look at the ECT term, but this one is a single equation approach. How about the Johansson and Just series? So as we observe in this screen, this is an EViews representation for my each equation because it's a vector error correction model. So how many variable I have just now? I have 4, right? Yeah, I have 4 variable, which consists of the money, income, interest rate, and exchange rate. So I will have the 4 equation, 4 different equation. Am I right? Yeah. 1, 2, 3, 4. So this is how we read the representation output. I have 1, 2, 3, 4 equation. Then this is a error correction model for the when the money as a dependent, and this is an error correction model when the income as a dependent, and then accordingly. So what is the purpose I want to use this representation? Because I want to know which is the coefficient I have. Coefficient. Because now I want to test whether the interest rate is it granted cost the money. So I want to test actually is C4. C4. Because you look at the coefficient here, actually is an interest rate is like one, right? Yeah, this is the long actually this is referred to the ECT lah. This refer to the ECT, right? Error correction term, like one period, and this is the constant value. Actually, no, sorry, this is C6 is a constant value. This actually is y head lah. T minus 1 is actually refer to the error correction term, flat one period. So what I want to test is a C4 because I want to answer the question whether the interest rate is it granted cost of money or not. So I look at the interest rate coefficient, which is C4. Whether the C4 granted cost of money, right? If I ask another question, is this the money granted cost the interest rate? So I look at the interest rate equation and look for the coefficient for the money in the short run, which refer to the changes in the money lag one period, right? Because it's a one lag. So it's a C14, C14 on the interest rate. So actually what is the test I'm going to test it? Actually, it's just use the t-test to see whether the C4 is it significant or not significant. And is this C14 significant or not significant in the equation number 3 here? So this is the VEC. Actually, if we represent in the system, this is a vector error correction models, right? So now, actually, I need to, because different people will have a different number of the coefficient. The number means that, let's say here is C4, right? Because it depends on how, which variable you, because it's very sensitive with the order. So if you put the income at the back, then actually the order for this coefficient will change lah. So I want to double confirm, go to the view, and then no, go to this one, sorry, go to the view here, representation. So once you click on the representation, actually this is the what we say the VAR models, right? This is the VAR model we discussed, and actually what we interest is this one, right? What we interest is this one, the VAR with the substitute coefficient. So you can copy this one and then I paste it in the previous output here, that easy for me to refer. So actually in the first equation, I would like to test the what we say the interest rate, right? Or test the interest rate, which is the oh, this is a quite different, I can't compare. Let me see. Yeah. I think I missed one step. That's why I cannot see the thing clearly. Actually, I need to go to the prop mix system. Yeah, this is the representation for your VAR. So I need to go to the prop and then mix system and order by variable. Yeah, this is the equation. This is the equation I'm looking for. Yeah. So I have to follow the step, choose the order variable, and estimate, see the representation. So estimate and then see the representation. Again, go to prop just now, right? Go to prop just now, prop, and then make the system order by variable, and then you estimate, right? estimate. You estimate, then you can see the result. But before that, this is my representation. So see whether same or not same. Yeah, so this is my money, right? And this is my ECT, right? Yeah, this is my error correction term. And actually it's a C3 lah. C3 in my C3 in my current exercise C3, because I put the I put an income first, right? I estimate the income first, only followed by the interest rate. That's why in your notes is C4, but in my exercise now actually it's a C3. I want to test a C3 lah. Then if I want to test the other way around, the interest rate will be my dependent, and then I look for the money coefficient, which is a C8, right? Which is a C8, which is the C8 in the my money equation, my interest rate equation. Okay, so why C8, but here is C14? Because this one is estimate the income first, right? Only followed by interest rate. But in my new estimation is followed by interest rate first, only by income. So the number of the coefficient will change accordingly, but the exact value for the coefficient will not change lah. Okay, so I go to the estimate just now and then click OK. You just use the method. When you scroll down, right, got a lot of method here. I use OS, then you click OK. So once you click OK, you can see the range, the coefficient range from C1 up to C24. Then you ask what is the coefficient 24 stand for, right? Actually, coefficient 24 is stand for the constant in the exchange rate equation. How about the coefficients C1 just now? Coefficient C1 just now is the ECT for the money equation. Okay, so this is the what we say the coefficient ECT lah. C1, C7. C7 is the ECT for the interest rate equation. C13 is the ECT for the income equation, and C19 is the what we say the ECT for the exchange rate equation. So now, if I want to estimate with the same like what the models I discussed here, money income, right? So okay, I re-estimate again. I go to the money income interest rate only followed by the exchange rate. I open them as a system, right? It's a system. Then you click OK. Yeah, OK. Oh, sorry, it's not system. It's open them as a WA. It's not system. It's a WA. That is I need to choose the ECM. Then that is 1 because I want to replicate something like the same coefficient we discussed that easy for you to follow. So again, I go to the proc. I go to the make a system that order by variables. Yeah, make a system order by variables. And then I go to estimate. Then this is a result similar with what in the notes lah. Then you click OK. So this is the result. Exactly same. C1, C14 is the constant for the exchange rate equation. Okay. So like this. So we'll have a scene. So the highlight in the yellow color one actually is the ECT. ECT for each equation. This one for money equation is negative 0.64. Then how about income? C7 is the ECT for the income equation, right? And negative 0.66 is the coefficient, is the ECT for the interest rate equation. That is very clearly shows that the ECT in the money equation actually is negative and significant, right? Negative and significant also apply to the ECT in the interest rate equation, as well as the ECT in the exchange rate equation, right? So, so what is my question just now? Is there a causality between the interest rate and money in the short run? So if you want to look at the causality between the interest rate and money in the short run, so we need to look at the C4 and the C14, whether significant or not significant. So the result shows that there is no causality between the money and interest rate. Why? Because if you look at the C4, C4 is not significant, right? With the p-value 0.45. And how about C14? C14 also not significant with the positive coefficient, and this coefficient actually is not significant. So if there is a insignificant result, so it means that there is a no causality between this interest rate and money in the short run, right? So then the question will ask you, how about the what we say, the long run causal, right? So if you want to look for the long run causality, actually we can look at the ECT, right? ECT. So which ECT carry the negative sign and significant, right? Which ECT carry the negative sign and significant? So we can look at the ECT. So which ECT? So the answer here shows C1, 13, 19, right? C1, C13, and C19. So C1, yeah, C1 is negative significant, C13 negative significant, and also the C19 negative significant. So these three ECT are significant. So what we can conclude here is these three ECT actually carry negative sign and significant. There is a long run causal. There is a long run causal from for these three equations. For these three, except the C7, except the second equation. There is a long run causal for the money, for the interest rate, and for the real effective exchange rate equation, but not applied to the interest rate equation. Okay, so this is how we look at the long run causal. So now, how about the ARDL BAO test? Because the idea if you go through our journal articles, there is the articles proposed by this actually this is a test proposed by Pasaran 2001. You can go through this Pasaran 2001 and then try to understand what it means by the BAO test, right? Actually, I think majority of you already go through this a little bit analysis, right, with the ARDL BAO test in the previous semester. Perhaps you can go through the original paper, which is published in 2001, to discuss about the idea behind the ARDL, right? Then for the empirical side, you can refer to all these papers. They will detail out actually the motivation for this ARDL and how they can apply in with the real world data. Besides that, actually, as you observe, there are several something like YouTube video, right? So you can go through it, right? You can go through the video. The first video here is to talk about the causality with a single equation approach, which we covered last week. And this week we also cover this one, causality test with the VECM. So you can see there is how to test the short run causality by using the Johansson and Just series. So later on we will use the ARDL BAO test and then test the causality based on the ARDL framework. Not only that, we also can test what we say the long run as well, right? Based on the ECT just now we discussed whether there's a long run causal or not. Then you also can go through this how the YouTube show you how to run the VECM estimation. Then another video actually combine what we discussed in the last 2 weeks about on this unit test, right? And also show you the details on how to perform the ARDL BAO test, done together with the ECM. So these are the things covered in this field, YouTube lah. So by the way, so let us perform the by using the ARDL BAO test, show you how to perform it. Actually, the idea behind the ARDL is very simple because why we have the ARDL, right? Because and still remember the first co-integration test is the Engel and Granger. Engel-Granger is a single equation approach to the co-integration, right? So then this single equation approach, then slowly we discuss about this Johansson and Just series, right? to allow to, I mean, what we say, the to account, not say to account lah, to become much more complex analysis, right? Not say much more complex, to much more complete analysis by taking into account the what we say, the exogenous variables. Instead of single equation, we're going to have the multiple equation, right? Right, and presented them in a vector form. So that's why you can see the chronology, right? Because of this unit root test, because of this the discussion, the debate in this unit root, then the limit, one of the limitation in the Johansson is the test is only applicable or only robust if your variable are I1. So if there's a mixture of I1, I0, the Johansson and Jeserich test actually is no longer accurate. That's why the Pasaran come up with a new co-integration test just for the small sample size. Just for the small sample size. And I cannot say small sample. Maybe I can say it's also valid if we apply with a small sample analysis. Because this there is another critical value proposed by Narayan in somewhere in 2001 as 2002, 2003 as well to complement the critic in the Pasarans, because in the Pasarans 2001 is only there is a critical value, but the critical value is for the huge sample. So if your sample size is very small, then Narayan come up with a simulated critical value. That's why you can see the difference between these two tests, the single equation approach as compared to the multivariate approach. So, so you go to the estimate the equation, go to the ARDL. So how we can run the analysis? We need to go to the open them, right? I just now open them as a var form. Then the method is a single equation, right? But now we can open them as a equation. So again, the money as the dependent, followed by income, interest rate, and exchange rate. Then the method here, when you scroll down, we look for the ARDL. So for those first time to perform analysis, actually the ARDL is a single equation. So we choose the ARDL, which actually stand for the autoregressive distributed lag model. So you click on the button here. Then for the first column, for the first box here, actually is you can see is for the linear dynamic specification. Then your dependent variable is the loan for the money, followed by the regressor, which include the income, interest rate, and RER. This is the fixed regressor specification. So once you scroll down for this test specification, actually refer to whether for this fixed regressor specification, whether you include the restricted for the constant or restricted for the trend as well as the trend. So these are the something like the what you plan to put as an additional not a variable, either is a trend or constant inside your test inside your regression. So lag length. So one of the issue in the ARDL is how to select the lag, right? So you can choose the automatic selection by the system, but we have to identify what are the maximum lag. So if you put the maximum lag is 4, regressor is 4, then the system will give you the models that which provide us the minimum value for the the minimum values based on the automatic selection. So let's try and see if the maximum lag is 4, whether do we have enough degree of freedom to perform the analysis. Before that, once you click on the option model selection criteria, against AIC will have a more penalty than the SIC if you apply the AIC for the small sample. So I would like to use the SIC, the Squash information criteria. Then you just click OK. Once you click OK, this is my ARDL models, right? ARDL models, which my dependent variable is a log for the money. Then I have the log money Blackman period. I also got the income, interest rate, right? And also the respective lag for the interest rate together with the level for the exchange rate. So these are the what we say the ARDL's models, but not yet finished, because once you estimate, you can go to the estimate equation. If the question asks you whether the interest rate is it granted cost the money, so which are the coefficient for the interest rate? A lot, right? C3, C4, C5, C6, C7. C8 is for exchange rate. So it means that you are testing all these coefficients, whether going to affect your money or not, right? Money or not. So how are we going to test the coefficient, whether equals to 0 or not equals to 0, right? So you can use the F-test. You can use the F-test to test whether the interest rate is it going to granted cost the money, or the other way around, or the other way around. Interest rate no granted cost the money, or interest rate granted cost the money. So interest rate no granted cost, or interest rate granted cost. How are we going to test the first hypothesis? Look at the coefficient. So here I'm put C3, C4, C5, C6, C7 equals to 0. Actually refer to the, when you open the representation, is C3 up to C7 equals to 0. I'm test all these coefficients, whether equals to 0, not equals to 0, to test whether the interest rate is it going to granted cost the money or the other way around. So for this, so how are we going to conduct the test? So C3 up to C7, right? I go to the e-views here. Then I can go to the I can go to this what we say the quick. Oh, sorry, not quick. Go to view and then go to the coefficient diagnostic. Coefficient diagnostic. Then look for the coefficient restriction. Coefficient restriction. But before that, try to double confirm whether is it C3 up to the coefficient I mentioned just now. Go for the representation. Refer to the coefficient for the interest rate. Yeah, from the C3 up to C7. Up to C7. So go to the view, diagnostic for the coefficient, and then go for the coefficient for the restriction. C3 equals to C4 equals to C5 equals to C6 equals to C7 equals to 0. So I want to test by using the word test to test whether the coefficient for this interest rate either equals to 0 or not equals to 0. Then you click OK. So the result returned me is the significant at 5%. Significant at 5%, 3.2679, together with the p-value 0.0166. So is significant at 5%. So you reject the hypothesis at 5%. So I can say that interest rate granted cost the money, right? Interest rate granted cost the money. So the conclusion is the interest rate cost the money in the short run. So this is a result for the short run. Why? Because the result is for the short run, right? C3 up to the C7 is for the short run. So now, how about if the question asks, is there a core integration or not? So just now is testing for the Granger causality. So how about is there a core integration? Because the Johansson-Jusserius were actually in the last week we discussed Johansson and Jusserius got two test statistics, right? The trace and then the eigenvalue value. So how about the F-test? Means that the core integration test proposed by Besaran actually is called Bao test. Yeah, it's called Bao test. So means this is the result we're going to have. So as we observe in this screen, I have a test statistic. Then I have a 3 critical value here. 1% significant levels are 1%, 5%, and 10%. So 11, right? 11. Then you refer to the critical value here. So which one I should compare? Sample size is 42, right? Sample size 42. So I refer to the nearest one. So this is a 10% critical value. These are the 5% critical value, then these are the 1% critical value. So 11.65 actually is greater than 5.54, right? It's greater than 5.54. So actually it's fall in the, it means that is greater than the critical value at the upper bound, upper bound. So we can conclude that actually there is a co-integration, right? There is a co-integration. So we reject the nut of no co-integration, then so what we can conclude, there is a co-integration in the long run, right? It's a co-integration. So how I can test the this bound test? We go to the view here, then go to the ARDL diagnostic. We go to view, then go to the ARDL diagnostic, click for the bound test. So this is the result, which you can replicate my notes lah, 11.65, so greater than the critical value 5.54 at 1%, 4.088 at 5%, 3.454 at 1%. So okay, so this is the findings. So what next? So if the question asks you, is the interest rate gradual cost the money in the long run or not? How are you going to answer? So now is test for the short run. How about for the long run? Right? How about for the long run? You can go to the e-views here, and then look for the long run result. Right? Go to the view, and then go to the take a look. Long run. You can go to the error correction result. Is it? Yeah, error correction result. No, this is ECT. Look for the ECT. I would like look for the error correction result. Co-integration relation. Yeah, it's a co-integration relation. If the question asks you whether there is a long run gradual causality from the interest rate to the money, so you can go to the e-views here, go to view, and then check for the diagnostic, ARDL diagnostic, go for the co-integration relation, then this is the result, right? This is the result. So co-integrating coefficient, this is a long run result. So interest rate is 0.1136, right? But it's insignificant with the p-value 0.5921. So with the p-value 0.5921, so what you can conclude? You can conclude that the interest rate not gradual cost the money in the long run. So interest rate is not significant, so you're going to fail to reject. So what is the conclusion? Interest rate no gradual cost the money in the long run. This is your long run result. And the previously, this is your short run result. So in the short run, there is a causality at 5%. But in the long run, there is a no gradual cost from the money to the money in the long run. Yeah, there is a short run, but no long run. So how about when you go through our video clip, if the question asks about the strong causal, is there a strong causality? So actually, how are you going to answer that? For the based on the F test or T test or the ROR test we used just now, actually to test for the short run causality, right? Then for the long run causality, we look at the long run result, and to look at the long run coefficient, right? To look at the t-statistic for the long run coefficient. Then how about the ECT term we learned before, right? So if you want to answer whether there is a strong causality or not, you have to fulfill all these three. Strong causal. Not only test for the short run, not only test for the long run, also need to look at the ECT. If these three shows that there is a short run causal and there is a long run causal, also the ECT is significant and negative significant. So combine all these three, we can conclude that there is a strong short run causality. There is a strong causality from the interest rate to the money. Okay, with these three conditions together lah. So how I can get the ECT here, right? So how I can get the ECT here? You can go to the e-views, then go to view, then check for this what we say the error correction model, right? Go for the ARDL diagnostic and then check for this error correction result. Once you check on this error correction result, the second table here will show us the ECT, the error correction model. This is a single equation approach. It's different compared to the Johanson and Just series, right? It's a we have a vector, right? Vector error correction models. But this one is the error correction model for the single equation with the ECT negative 0.397. And this ECT is significant at 1%. So significant at 1%. So what you can conclude here. So do we have the short run causal? Yes, right. Based on the war test just now, there is the interest rate. The interest rate is granted cost of money at 5%. Is the ECT negative and significant? The answer is yes, right? So how about another one more condition? Is there a long run causal? The answer is no, right? The answer is no, because the coefficient here is not significant, right? At any significant level. So there is a no long run causal. So with this condition, actually there's a no strong causal from the interest rate to the money. No strong causal relationship. There is a granted causality in the short run, but no strong causal because no long run causal from the interest rate to the money. So these are what I want to you all something like understand about the causality in the vector form, as well as how we can apply the ARDL approach to test for the short run, long run, as well as a strong causal. So these are the things for the lecture 4. Okay, so I close this one. Okay. So now I would like to move to the another topic for today is this what we call the types of the panel regression, right? Including the POO ORS, right? If we have time, I will proceed to the fixed effect estimation. Okay, so let's look at the lecture 5, and also got another one. What is additional lecture notes, right? So the type of the panel regression. So in this topic, actually, we were going to introduce you 3 different types. One is the POO OLS, is it what we call as a pool ordinary square model. Another panel approach is called fixed effect estimation, which include the least square dummy variables estimator. So we also have the fixed effect estimator, and we will discuss some issue of the fixed effect model. There's another panel model which is called random effect model. So these are the 3 type of the panel regression. So what is panel data? So as we discussed in the first week, right, of the lecture, as you remember, right, we made online that day we discussed. So actually the panel is combined the time series and the cross-sectional, right? So not only time series like what we covered just now, also the cross-sectional data. So for example, just now I just focus on the Malaysia. If I focus on the money demand for Asian 5, actually, if I want to estimate the money demand for the Asian 5 in a panel setting, actually I combine the time series and the cross-sectional data, right? So on the same variable, same cross-sectional sample are followed over 2 or more time periods, right? So what the reason for using panel? So again, you can take into account the individual specific heterogeneity. You can compare data into 2 dimensions. So will give us the more information, more data variation. So there is no concern about the multi-connectivity, and we will have a more degree of freedom. Not only that, the panel data is better than the cross-sectional to study about the dynamic of change. Yeah, so this is the one of the reason why people move forward to the panel, right? And the panel also good to detect and measuring the effect, which cannot capture by using the cross-sectional or time series itself. So the panel data enable the study more complex behavior as compared to the time series and the cross-sectional. Panel data also minimize the effect of aggregation. Yeah, because sometimes they want to study in a aggregate level, right? So actually aggregate level going to have the aggregation bias. So by study the panel can minimize this bias. And by using panel also can increase the precision of the regression, because increase the power of the test, because it increase the number of observation, right? And also increase the information. So it tends to increase the precision because you will have a lot of degree of freedom. So increase precision. And you also can control for the individual specific effect. So why use panel? Only at least 3 reasons: increase sample size, provide insight which can't answer by just using a time series or cross-sectional, and to avoid omitted variable problems, right? Because when you study about the time series, the data might not available in the, for example, in a very complete times observation. So you make you exclude out that variables. If you study that particular variables, for example, just like I have 5 observation, but you study that in a panel setting, so you can avoid the omitted variable problems lah. So as we discussed last time, these are the 3 panel estimation. So what we're going to cover in this week and after semester break is on the pool OS, fixed effect, as well as the random effect. We're not going to touch on this micro panel, which include the system GMM, first difference GMM. That's what I'd like it to you. By the way, we already cover the time series unit, right? We also time series co-integration. So after the traditional approach, we're going to move forward to discuss on this panel unit, panel co-integration, as well as the mean group and the pool mean group. Okay. So again, this is the how we always said the balanced panels lah, right? Have the, if all the cross-sectional have the same number of time series, that is called the panel actually is balanced lah. So this is a metric of the balance panel, which is the no missing cross-sectional observation or the time series observation. So suppose Y is the investment and X is referred to the measure of profit. So, and then N here refer to I to N refer to the firm. So I refer to the firm, start from 1 up to the N firm, and then the T start from 1 up to the T is stand for the time period. If you want to investigate the investment on the profit, so this is your models, and in the panel is subscript IT lah, instead of I or instead of T itself, right? So it's a IT, it's a panel setting. So there are several assumptions to estimate the equation number 1 just now. So what are the assumptions? Assume the intercept and the slope coefficient are constant across the time and firm, and the error term capture the differences over the time and over the firm. So these are the several assumptions if you want to estimate the equation number 1 just now. Assume intercept and the slope coefficient are constant. And the slope coefficient is constant, but intercept might varies over the firm. Yeah. So it can be constant, but also the slope can be varies over the firm. The slope coefficient is constant. Yeah, the slope coefficient is constant, but the intercept varies over the firm and over the time. Not only over the firm, also over the firm and over the time, right? So there another assumption is the all coefficient varies over the firm. Not only the intercept, including the slope, they are varied over the firm. So how about another assumption can be made to if you want to estimate the equation number 1, intercept as well as the slope vary over the firm and the time. So these are the several assumptions. So let's take a look the first something like the graph representation. So this is an estimation option 1 on the list. Option 1, intercept and the slope are constant, right? So constant, intercept and the slope are constant. So only one regression line. Only one regression line. So if you assume the intercept and the slope are constant, actually this is a regression line, right? But the true model for the firm number 1 is here. The true model from number 2 is here. Number 3 is here. Number 4 is here. So my result in the heterogeneity bias, right? Because different firm might have a different response, right? From what we say, the profit on the investment. So different firm will have a different reaction of their profit on the investment. That's why they have 1, 2, 3, 4, 4 regression line instead of 1. So if you estimate by using the pool regression, or we call it as a pool OLS, might result in a heterogeneity bias. So how you going to solve this? So that is one method, which is called least square dummy variable. Is a method used in the econometric to estimate the coefficient of the linear regression in the presence of the categorical variables. So the categorical variable is a set of binary or the dummy variable where each dummy corresponds on the level of the categorical variables. Okay, so let's see how it works. So the dummy variable take on a value of 1 if the observation belongs to that level and 0 otherwise. So take on two value, 1 or 0. Then you can use this estimator to estimate the regression coefficient just by using the OLS. Yeah. So what is the important consideration when you want to estimate this least square dummy variable estimator? Is the perfect multi-connectivity between the dummy. So you have to aware of this perfect multi-connectivity, especially between the dummy variables. Why? Because one of the dummy variable can be perfectly predict from the others. Because dummy variables, right, 0 or 1. So if there is a perfectly predicted by others, it might cause the perfect multi-connectivity. So how to avoid this? Adopt the rules that n-1. So one of the dummy variable drop from the model, serving as the reference category for that categorical variables. So let's say, for example, if I want to use 0 and 1 to represent for the gender, so gender is if I create 1 for the male, 0 for the female, so just just one dummy variable for the gender, right? If you create another dummy variable for the gender as well, this might cause the what we say the perfect multi-connectivities lah. So now let's take the previous slide suggests the better way to model the data would be allowed each group to have its own intercept. Just have a 4 or 5 regression line instead of 1, right? So how we can achieve that? So this is actually known as the fixed effects model. Fixed effects model. So just have the 5 regression line instead of 1. So how do we estimate it? So the simple way is allow each firm to have its own intercept. Is to create a set of dummy variables. Create a dummy variable. So one for each firm and include them as a regressor. So you can see the difference between equation number 2 and 3 is we have an additional variable here. This refers to a set of dummy variables. So this is also known as a least square dummy variable. Least square dummy variable. This is called least square dummy variable. And as we observe here, there is no constant in this regression, no constant. However, if there are a lot of firms, that becomes a very tedious to create all the dummy variable needed, right? So the method used is called the covariance estimator and work to be differentiating out the fixed effect by expressing the variables as the deviation from their group mean. Because there's a lot of the firm, so it's very tedious for us to create all the dummy variables needed. So we can use this differencing, right? Differencing. So we use the y minus the mean. It means that their group mean, subscript I for the group mean. Then each variable also minus the average, right? The average, the mean value for the x, as well as the mean value for the residual. So the further extension is to allow the intercept, right? Intercept vary across to the different time. So if you allow the intercept to vary across the different type, this one we call as a two-way fixed effect lah. So just now it's a one-way fixed effect. If you also allow the intercept to vary across the different time period, This we call as a two-way fixed effect. So how you going to achieve that if you have to include one more regressor in your equation number 6? Means like your equation number 6 lah. So this is the dummy variable we discussed in the equation 3 just now. So equation 3 just now. And with the additional time train here to allow intercept to vary across the different time period, then we have an additional variable here in the equation number 6. So makes it simple. Actually, fixed effect is another method to eliminate the time invariant unobserved effect. So eliminate the time invariant unobserved effect. Eliminate. So how it works? So consider the following model. I have my dependent and x1, x2 until xk, right? And a here. So the correlation between the fixed effect, I mean the a, and the explanatory variable will cause the bias lah. So the fixed effect and the explanatory variables will cause a bias in the estimate. So we need to eliminate the a from the estimation. Yeah. So the first difference is one method. So we first difference so another method is what we discussed before and present as follow. So you compute the means, right? You compute the mean for the each variables. Then you use the deviation, right? The y minus the mean, right? Then you have a following equation, which is equation number 8. Since the a is constant, right? So does not do not have the over the bar lah, because it's a constant here, right? So now you can subtract the 8 from the 7. So it is 8, right? From the 7 here. So you can subtract the 8 from the 7. This sample, right? Sample average for the each variables. So you subtract the equation 8 from the equation number 7. So you will get the following equation. So the original one minus the mean, right? The mean for each variables. So get the deviation, get the difference lah. This is a difference approach. So this transformation actually you eliminate the fixed effect. So you eliminate the fixed effect, and it's called the Wien transformation. This transformation is called the Wien transformation. So with this transformation, actually we eliminate the constant as well. So the constant is disappear, right? In this equation, it's disappear. It's still here in the equation number 8. In the equation number 7, still here. But because of this Wien transformation or elimination, so the constant actually disappear. So now we simplify the notation. You can rewrite the above equation as follow. As the equation number 9 here. So your y, your x1, x2 up to xk, and your residue. So we have a dot here, right? Actually, is a called time demean. Time demean. Time demeans the data on the y. So you also can apply the same notation for the x variable as well, right? So the time dummy coefficient is allowed for regression function to shift over the time to capture the changes in the technology. Because we understand that the changes in the technology, right? Government regulation, tax policy actually is the time, right? For the time. So that's why the time dummy coefficient can allow the regression function to shift over the time to analyze the government policy, especially the tax policy, the changes in the technology, etc., as well as the wars. So allowing the intercept and the slope coefficient to vary across the group, right? We also can allow the intercept and then the slope coefficient to vary across the group. If you have a sufficient long time series to the panel, we sure can estimate a separate OS law for each group, right? Yeah, if you have a sufficient long time dimension, you have a long enough, so we can estimate them one by one, right? One by one for each group. But it's very tedious, right? If I have a 50 firm, am I going to estimate 50 times? Because each firm will have each equation, right? 50 times. So how about if the number of firms is small? If the number of firms is small, then you can estimate a single regression with the interaction between the X and the group dummy variable. Yeah. So this is called cross-section dimension, right? So if the number of firm is small, you can estimate a single equation with the interaction with the between the X and the dummy variables. So you can estimate the d-mean equation number 8 just now. This one, number 8 just now. Using OS, and this is called fixed effect estimation. I think it's not number 8, number 9, sorry. If you estimate number 9 now, then by using OS, this is called fixed effect estimation. Again, OS, right? OS, if my variable is I1 or I0, is it going to have a spurious regression? Yeah, this is the thing we're going to cover after semester break lah, right? So bear in mind that fixed effect estimation is estimates by using OS. So you just run the OS with the following equation. It's called fixed effect estimation, right? Fixed effect estimation, because it's a deviation from the mean, right? For each variable, it's deviation from the mean and no constant, right? No constant. Okay, so that is the point that if you ignore this fixed effect, you just estimate the one regression, right? Actually, it's a bias. Actually, it's bias if you just estimate this equation 9. In fact, there is a different firm should have a different regression line, right? So there is a bias from ignore the fixed effect. So example here, you can see the example here is in a single year, the cross-sectional model, the murder rate appear to increase with the execution. So this is the total execution in the past 3 years. Then this is a regression line. So you can see the murder rate is appear to increase, like the murder rate is increased with the execution. Okay. So if you use the fixed effect, to estimate it, the murder rate decreases with the execution. So it means what? It means that because of this omitted variable bias, right? If you omit the fixed effect, you will tend to give you the different conclusion. Actually, the murder rate appear to decreases with the execution, like this. But you ignore this fixed effect, it might create a opposite result lah. That's why I give you the different conclusion. It's very weird, right? Murder rate appear to increase with the execution instead of decreases. So that is the story why we want to take into account this fixed effect. Actually, there are several issues as well by using the fixed effect. So bias, yeah. One of them is called bias because the fixed effect assumes the unobserved heterogeneity is time invariant. Assume the unobserved heterogeneity is time invariant. But if this assumption is warranted, the model can produce bias estimates. Yeah. So this is one of the limitation bias. Efficiency. The fixed effect model can also be less efficient than the other, such as the random effect, because normally we will compare the fixed effect together with the random effect, right? Together with the pool OS. So the fixed effect can be less efficient compared to the random effect, which assume that the unobserved heterogeneity is uncorrelated with the independent variables. So that is one of the limitation as well, right? So one of the issue is bias. The other one is talking about the efficiency. Also, the third one is the time invariant variables, time consuming, as well as the limited variation. Because the fixed effect cannot account for the time invariant variables such as the gender or race. So if you have the variable like the gender or race, actually it's a constant, right? So it might make your estimation become very weird, right? Because these are the variable is time invariant variables. So when you want to estimate using the fixed effect, you have to be careful. You have to understand well your data set. Is it your data set is a time invariant variables, right? So you only can use that variable as a control only, cannot be the main variables. Another limitation is the time consuming. Because you estimate the fixed effect model can be time consuming and computation intensive lah, right? If you have a very huge data set, and the fixed effect can also be limited by the variation in the data set. So limited variation. So this another limitation. Or what we say another challenges you have to take into account if you want to adopt this fixed effect, right, with your data set. So so I think that's the things I would like to stop here. So next, after you can go through our lecture slide. You can go through the lecture slide here, and then follow the lecture slide and also the additional notes on the lecture file to estimate the panel mod data with the eViews. You follow the step here. So maybe I briefly discuss about the what we say the models, because after semester break I can touch on this fixed effect, right? Because one of the next chapter going to touch is on the fixed effect models. Oh no, it's a random effect model, because we already talked about this OS, pooled ordinary square. Then we also got discuss a bit the least square dummy variable, right, estimator. Then just now we also got discussed on this fixed effect estimator. Then followed by some issue of the fixed effect models. Then next week we're going to discuss on these random effect models. By the way, I will something like what we say, you can follow the step to in this lecture notes, as well as the additional lecture notes for lecture 5 to do some analysis by using the eViews, right, to estimate the investment function with the POS and the fixed effect model. Then after semester break, I will touch on this random effect together with the Busch-Bertrand test as well as the Hausman test, right? So let us briefly discuss this investment function. So the Granville, right, consider the following investment function for the time firms. So how to read this equation? We have the investment is an investment function, and then I have the constant, I have the VAL. VAL refer to the market value of the stock, and the CAP refer to the capital stock, and the epsilon here refer to the residual. So the 10 firms is represented by the I here. Then this is a panel equations panel model. How I know this is a panel model? Because the subscript IT here, right? For each variable, subscript IT. And for the I equals to 1 up to 10. So I have a 10 firms, right? Because it refers to 10 firms in the US. So so GM, US, GE, CH, AR up to DM. These are the 10 firms in the US. Actually, this is the data I draw from this Granville. Is actually is which is the in your spectrum. We call it as a available in the Excel sheet as well as in the eViews work file. It's called the file name is copy of the Granville. So once you open it, it's a copy of this Granville, right? So we have this 3 series, only 3 for the investment series, CAP, and the VL. So there's a question mark here. Question mark in the eView is represent for the panel. So later on, after semester break, I will show you how to analyze by using the eViews, right? So it's a question mark is represent for the panel, and it starts from 1965 up to 1954, right? So got start with the GM and then followed by the US, then followed by the GE. So you can see how the how I stack the data, right? How I stack the data, stack it. So this is one firm for these 3 series. If I just estimate investment CAP and VL for the GM, this is just a time series, but now it's a panel, right? So a little bit different compared to the previous setting. So I will follow by another three series for the US case, right? Start from 1935 up to 1954, right? For the US case, this is another set. So you can see totally 10 now. So this for the GM, for the US, followed by the GE, and then followed by the GH, right? These are the data sets I'm going to use. So what else I want to cover is yeah. So you can estimate the investment function with the POS and the FE and the FEM. So you can follow the guideline here. Actually, so it's following the investment function for the 10 firms. So you need to create the work files, right? You can use the eViews to help you create the work file, follow the step here, then create the pool. Then after that, estimate, right? Put in the variables and then you estimate, stack it, and then you estimate. So this one I will show you some in the after semester break. So what I want to cover right now is where's the next slide. So it's the random error models. Yeah, so let me see. Okay, perhaps I finish up this random error as well, right? Then next week straight away go to the estimation. So now, so there is another type of the panel which is called random effect model, or another name actually is error component models. So what is the difference compared to the FEM? Later on, we will see the differences. So the fixed effect models assume that each group has a non-stochastic group-specific component to the Y. So including the dummy variable is a way to control this unobserved effect. So to this fixed effect, but this unobserved effect may be stochastic, might be random. That's why the random effect model come in. So the random effect models attempt to deal with this stochastic unobserved effect, right? So that's why the difference compared to the previous model is not only A, we also got the UIT, the residual IT. And this term, there is an unobserved component, which is the A, is treated as the component of the random error, right? So as a random error lah. So it's an element of the error which varies between the group but not within the group. Yeah, it's varies between the group but not within the group. It's between but not within. And the U is the element for the error which varies over the group. So we have the VIT here. So this is the difference compared to the fixed effect model, because it's tackle also the unobserved effect, means for this stochastic unobserved effect, which is random. So what is REM? REM actually assume constant is a random variable with the mean value of the beta 0. So random effect model assume constant is a random variable. So how about intercept? Intercept for the individual will be beta 0i equals to beta 0 plus the AI. So the constant will be beta 0 plus the AI here, plus the AI. So substitute into the original model, we'll obtain the equation 10. So it means that substitute this beta 0 plus beta, means that plus this AI, we can obtain this equation number 10 here lah. So from this equation 10, we observe that there are two components. So this is called composite algorithm. This composite algorithm consists of two components, which is the AI and the UIT. AI is a cross-sectional error component. This one is a cross-section error component, and the U here, UIT, is referred to the individual specific error component. So there are two components. Which called composite algorithms. Composite algorithm. This composite algorithm include the AI and the UIT. What is AI? Cross-sectional error component, as well as the individual specific algorithm. Okay. And these two components actually is the idiosyncratic terms which varies where across the cross section and time. And these some assumptions. These are the several assumptions about the random errors, random what we say the random effect models, including their mean for the residue equals to 0, their homoscedasticity, and independent of the two components, no autocorrelation, and no across group correlation, and also there is no correlation of the regressor, the residual, and the independent variable equals to 0. The difference between the random effect and the fixed effect is the random effect cannot be performed by using OS. Yeah, we can, because just now the fixed effect is estimated by using OS, but the random effect cannot be performed by using OS. It can you only can estimate by using what we call as a GLS, the generalized least square method. Okay, so let's take a look back the equation 10 just now, the unobserved effect model, right, with the VIT here. Previously we applied the fixed effect estimation because we suspect the AI are correlated with some of the explanatory variable. If we since we expect the AI are correlated with some explanatory variable, right? But if we can assume that the AI are not correlated with any of the explanatory, so we can estimate the model more efficiently. So we assume this one correlated with other independent variables, right? If we assume are not correlated, then we can estimate the model more efficiently. Okay, more efficient means that you are able to get the smaller standard errors. So if the AI are not correlated, then you just simply use the pool OS, right? Because if the AI not correlated with the other independent variable, then I just simply use the pool OS, right? The pool OS will be consistent. So what it means? It means that if the AI are not correlated with any independent variables, I just can proceed with the pool OS because the pool OS estimation will be consistent, right? But the problem is now the serial correlation, right? Serial correlation, the composite error term VIT here, and also the other period are correlated. So we have to consider about the serial correlation. Serial correlation. So to be more precise, we can take a look the correlation between the independent variable and I equals to 0 for the time t1 up to t, and also the j is up to the k. So if the AI is uncorrelated with all the, it means that if assume equals to 0, so the AI there's no correlation between the AI with the x, right? Then OS is consistent. OS estimation is consistent. In addition, we assume that the AI and the idiosyncratic error in all the periods are uncorrelated. So then we can show the following correlation for this VIT and VIS refer to two different periods in all the two different periods. So it's not equals to 0, right? Uncorrelated. So the sigma power 2 and also equals to the variance for the AI, right? So these refer to the same now. A sigma power 2 actually equals to the variance for the A. So estimator might be efficient if we ignore this correlation. So you have to take into account this correlation, what it means. So later on in the estimation, might provide you much more clearer picture when we estimate the fixed effect and random effect, right? Yeah, we will give you the much more clear picture when we have a hands-on analysis. Okay, so now what are the advantages and disadvantages of the random effect? Advantages is more degree of freedom than the fixed effect, because in this fixed effect we have a lot of the intercept, right? Yeah, so you will lose a lot of degree of freedom. But by using this random effect, so you have a more degree of freedom compared to the fixed effect, because rather than estimate and intercept virtually every cross-sectional unit, now you just estimate the need to do is just estimate the parameter that describe the distribution of the intercept. You also estimate the time invariant explanatory variables. You can estimate the time invariant explanatory variable. So it means what? If your variable series, if you estimate, for example, want to see the impact of the race or gender on certain on particular dependent variable, if you understand that the variable actually is a time invariant, then I will advise you to run this random effect, because this is one of the guideline. If you have this time invariant explanatory variables, it advises you to run the random effect models. So what are the disadvantage? Disadvantage for this random effect is require us to assume the AI is uncorrelated with the independent variable, because to avoid the omitted variable bias. Just now, if the AI is correlated with the X, right, then there's a problems, right? So you have to assume they are uncorrelated. If we're going to, means that to avoid this omitted variable bias lah. So this might be a very strong assumption lah. So now recall that the fixed model is based on the assumption that the cross-sectional unit has its own intercept, but the random effect is based on the assumption that the intercept for each cross-sectional unit is drawn from the distribution. It means that it's a random. So each intercept is a random draw from the intercept distribution, and therefore is independent of the error term for this particular observation. So there is the what we say the difference between these two. So what are the issue? Also almost similar issue with the phase effect. But then you can see the differences after you go through these two slides. Endogeneity. The random effect assumes that the unobserved heterogeneity is uncorrelated with the independent, right? Uncorrelated with the independent. But if this assumption warranted, the model actually produces bias due to the endogeneity issue. It might have an endogeneity because the AI might correlate with the independent variable. Then the specification issue, because the random effect model requires specific assumption about the distribution of the random effect. Actually is warranted. If this warranted, right, then might create this could create the bias in the estimate, right? And also the issue of this efficiency. Yeah, it's less efficient compared to the phase effect, because if you have the unobserved heterogeneity is time invariant, right? Issue of classification and also the efficiency. Also limited variation, like the phase effect. Also random effect model can also limited by the variation in the data. If there is a little variation in the independent variable, you might not be able to estimate the coefficient accurately. Right? And interpretation, because the coefficient in the random effect interpreted as the average effect of the independent variable, so it might be not so very difficult to something like interest, like in order very difficult to interpret, because it's just a average effect of the independent variables, right? So that is the thing, because the common intercept, remember the common intercept actually is a mean value of the all the cross intercept plus the error term. So this is how this is how we go in the estimation. If the question asks about how to compute the intercept in the random models, so actually it's a mean value of all the cross-section intercept plus the error terms. Oh no, sorry, plus the error component. This is the formula for us to get the common intercept. Okay. Actually, there is the how to choose between the fixed effect and random effect, because pool over S, there are three different type of the traditional panel estimation, right? So how to choose between the pool over S, fixed effect and random effect? So the judge at all, right? So if we have a large T and small n, and so the fixed effect is preferable. So it means that in the panel estimation, if you have a many observation, but just a few firm, then fixed effect is preferable. How about large n? If you have a many firm, but only small t, then random effect is preferable, right? So how about if the error component is correlated with the X. Because just now the assumption, right? The assumption for the random effect is the result will be biased if the V is correlated with the independent variable. So if the V is correlated with the X, then random effect model is biased. So preferred is a phase effect. How about for the large N and the small t? If you have a many firm but very short sample, assumption behind the random effect hold, but in whole, then the random effect is much more efficient than the fixed effect. So for the there are the several something like the guideline for us to follow if you want to use this to help us to choose between the models. Okay. So again, these are the same models we're going to discuss. So discuss how to for the illustration, how to estimate the investment function with the fixed effect and as well as with the random effect. So you can the step is we're going to discuss after semester break. By the way, you can go through the step here, right? So today we just talk on the theory side. Then for the if you want to go through like the deep understanding about the random effect, phase effect, and the pool OS, you can go through the journal articles like the journal articles I uploaded in the Spectrum. The paper in the journal one is published by the International Monetary Fund, which is talking about the investment in the WAEMU. You can see how they estimate the models with the random effect, fixed effect, right? We also have a journal 2 is talk about the panel approach to study the relationship between the economic growth and the FDI in Asia. So this is how they report their result with the fixed effect, random effect, together with the test going to show you next week. Hausman test. These are Hausman test. So this is the result. They summarize the result in the table. So okay. So next week we're going to examine the Hausman test. No, right. Next week we're going to show you the how to estimate the investment function with the fixed effect, with the pool OS, as well as the random effect, together with the Hausman test. Yeah, so to see is it random effect better or random effects better or fixed effect models better? And we're going to evaluate the sum panel data model as well. So that's only for, I think that's only for today's lecture. So please go through the additional lecture notes for this lecture 5. Then you go through, then to each our analysis for the next week lecture. Okay, see you all next week. Bye bye, and enjoy some not next week, right? After semester break. Yeah. So see you all after semester break. So enjoy your semester break and have a nice holiday. So see you all after semester break. Bye.